Section 11.4 is on page 767, talks about the comparison test. Actually, it has two tests in it. It has the comparison test and the limit comparison test. Today we're going to get the comparison test out of the way. Here, comparison test states, suppose you have two tests in which those tests consist of positive terms. You can only use terms if you're dealing with positive terms. Then it says, well, if you take this series to be, the way they write it, kind of awkward, I'm going to rewrite it. They say if a sub n is less than b sub n, and the bigger converge, then the conclusion is that the smaller converge. And they switch. If a sub n is bigger than b sub n, and the smaller diverge, then the bigger diverge. So I'm going to rewrite that really quick. I'm going to say given, that's an awkward given the series from n equal 1 to infinity of a sub n and the series n equal 1 to infinity of b sub n, right? If a sub n is less than or equal to b sub n for some n. And if the series of b sub n, okay, I am stuck on that n. If the series of b sub n converge, then the series of a sub n converge automatically. Remember, the assumption is that we're assuming b sub n is always bigger than a sub n. So if the bigger converge, the smaller converge. And also, if I look at the series n equal 1 to infinity of a sub n to diverge, then I assume the series n equal 1 to infinity of b sub n will diverge as well. Again, if the smaller diverge, then the bigger diverge. There are two cases you gotta be cautious with. Be careful. Note, if under the same conditions, if the series n equal 1 to infinity of a sub n converge, then the series n equal 1 to infinity of b sub n clueless. If the smaller converge, that doesn't mean anything. And if the series from n equal 1 to infinity of b sub n diverge, if the bigger diverge, then the conclusion about the smaller is unknown. It could converge, it could diverge. And we're going to start playing with those, but we're going to do this slowly, at least in the beginning. This is how it works. Whenever I'm dealing with rationals, radicals, anything that I can get rid of a value, that is, I'll get rid of the numbers. And you want to start this way in the beginning. It takes time, but you'll get better at it. So start with always what's given on the left, that's how I prefer it, and the right, without the number. Just get rid of the number. Which is bigger? Remember, n is always bigger than or equal to 2. Wouldn't this be bigger than that? Always start that way. And when you put 1 over, guess what? That will switch. In the beginning, you should do that until you get the hang of this. Now, if I look at this, this is 1 over n to the 1/2, right? That sequence converge. Series, you guys, if you look, it says if you compared the series, you show the sequence is bigger or smaller, the conclusion is on the series, not the sequence. So you must put that series there. Well, guess what? P equal 1/2, less than 1. Therefore, this diverge, right? I'm going to change the format of this a bit. Actually, no, I'm going to leave it as is. So what did I show? I've just shown that this series is smaller than this. And I've shown the smaller diverge. Therefore, the series n equal 2 to infinity of 1 over square root of n minus 1 diverge by the comparison test. Now, I do want to point out, this says 1 to infinity, but if I go from 2 to infinity, does it matter? No, it doesn't matter. Because if this diverge and you add one term to it, it's not going to make a difference. It's going to still diverge. So, if I look at problem number 6, I'm going to start again in steps. Just take your time. Make sure that this is positive. Now, when you put n equal 1, you get 0. 0 is not positive nor negative. I'll let that slide. And here, if you let n equal 2, that's positive. I forgot to mention that. Make sure it's positive if you're going to use the comparison test. Well, I'm going to start with the denominator because that's the messier. N cubed and n cubed plus 1. Isn't this bigger? And I'm going to go in order. Putting 1 over, we'll switch that sign. Very good. I'm going to take an n, add an n, and a minus 1 and a minus 1. Not a problem. Now if I look just at the top, if it works for my benefit, that's really good. If it doesn't, then I'll redo it. You know what? Why does it do that always? I'm going to look at n cubed plus 1 and n cubed. N cubed plus 1 is bigger. When I put 1 over, that becomes less than. I'm going to tag the top. So multiply by n minus 1. That's not a problem. Nothing changes because that's positive. And now I'm going to try to see if I can get rid of that 1. If I can't, I could still do the problem, but it'll be easier if I put an n in there and n cubed. So basically, I'm comparing n minus 1 and n. Which is bigger? As long as the inequality is matching in direction, I'm in good shape, and that is 1 over n squared. And 1 over n squared converge. The series of 1 over n squared is a p-series. Well, we've shown that the bigger converge. Therefore, the smaller must converge by the comparison test. And what if that was the exception, like what I've shown you up there? Well, I'm glad you're asking that. What if it's one of those? I'm glad you're asking that because that's coming up. Just give it time. How about this problem? I have a couple of options on this problem. I could, here, if I want, take the limit as n approaches infinity, divide by the highest power term of the denominator. What is that called? Test for divergence. That will approach 0. So I'm looking at 1 minus 0. That will approach infinity, which will equal infinity, not equal to 0. Therefore, diverge by test for divergence. Now, you could if you want. So how often should you try test for divergence? You should try test for divergence on every single problem in this entire chapter. Every problem. Or, I could come in and say, you know what? I am gonna, I'll tell you what. I'll finish what I need. If I have time at the end, I'll come and do this the other way. Because I might run out of time. Let me move on to the next problem. If I glance at this problem, and I'm trying to figure out how this works, well, obviously I want to get rid of the number first, so I take 1 plus k cubed and k cubed. I know that 1 plus k cubed is bigger. When I put 1 over, those cancel out. Okay, and I'll tag the k sine squared of k sine squared of k. The reason I can do that because that's always positive. And I know this is less than. The biggest a sine squared could ever be is a 1. And that is 1 over, you know what I'm thinking, k squared. And I know that the series, this is a p-series, bigger than 1, therefore converge. Therefore, the series k equal 1 to infinity of k, the sine squared of k divided by 1 plus k cubed, converge by the comparison test. So, if you say converge without telling me from what, you lose most of the credit. I need to know what that is every time. And if I look at number 14, I'm looking at 3 n to the 4th plus 1 and 3 n to the 4th. This is bigger. And if I put 1 over, that becomes small. I could put a radical too. Might as well. And this is 1 over radical 3 times n squared. So if I look at 1 over radical 3, the series of 1 over n squared, p equal 2 bigger than 1, therefore converge. Therefore, the series n equal 1 to infinity of 1 over cube root of 3n to the 4th plus 1 converge by the comparison test. Okay, now let me go back and do that. It seems I have to have time in this video. So here, instead of doing what I just did, I could have said, well, let me look at that slightly different. Let me look at 5n minus 1 and 5n. This is definitely bigger than that. And when I put 1 over, that will switch. And if I tag on now multiply by 6 to the n, if you multiply by a positive, this inequality holds. This is 6 over 5th to the n power. That is geometric. R equals 6 over 5th, bigger than 1. Therefore diverge. And if the smaller diverge, therefore the CV's n equal 1 to infinity of 6 to the n over 5 to the n minus 1 diverge by the comparison test. So you could do this few ways. There's nothing faster than the test for divergence. Now I want to tackle one more problem, and that's not the end of the section. We're going to stop here. I would like to look at problem number 18. There are a couple of problems to look at. 18 is a nice one. They're all the same. So I proceed with 18 like I normally do. I'll say, okay, let's look at this. And let's look at this. Well, obviously this is bigger. If I put 1 over, that becomes less than, right? And I tag the 2. So if I look at 2 times the series of 1 over n to the 1/2, p is 1/2 less than 1, therefore diverge. But this is bigger. Therefore what? Series n equal 1 to infinity 2 over radical n plus 2. If you say diverge, you just got a 0. We don't know whether that converge or diverge. And if I get rid of anything else, it will switch and it will converge, then it wouldn't matter anyways. So the inequality can't hold on few problems, and that's why you need another test. We're going to stop here for now, and that's what you need to do for the next class.